It is my pleasure to introduce Dr. Ozbay. Okay. Dr. Ozbay joined the Civil and Urban Engineering at New York University Tandon School of Engineering and the Center for Urban Science and Progress as a tenured full professor in August 2013. He's currently the founding director of the C2 Smart Center. It's a Tier 1 UTC funded by a US DOT. Prior to that, Professor Ozbay was a tenured professor, full professor at Rutgers University's Department of Civil and Environmental Engineering, where he joined as an assistant professor in 1996. In 2008, he was a visiting scholar at the Operations Research and Financial Engineering Department at Princeton University. Dr. Ozbay is a recipient of the prestigious National Science Foundation Career Award. His research interests in transportation cover a wide range of topics, including data analytics for advanced technology and sensing applications in smart cities, development of simulation models of large-scale complex transportation systems, modeling and evaluation of traffic incident and emergency management, feedback-based online real-time traffic control techniques, traffic safety, operations research, application in network optimization, and humanitarian inventory control and transportation economics. He has co-authored 4 books and published approximately 400 refereed papers in scholarly journals and conference proceedings. Dr. Ozbay is an associate editor of the Journal of ITS, and he is a co-editor of several books. He also serves as associate editor of other leading journals, such as Transport Metrica B, the Transportation Dynamics Journal. Since 1994, Dr. Ozbay has been the principal investigator and co-principal investigator of more than 100 projects funded at a level of more than $20 million. The funding organizations include NSF, New Jersey DOT, New York MTC, New York State DOT, New Jersey Highway Authority, US DOT, Virginia DOT, and different university transportation centers, Department of Homeland Security, and US DOT ITS Research Center for Excellence. And he is my dear friend. I know him since he was a PhD student at Virginia Tech. So I'm very glad and honored to introduce my dear friend, Dr. Kaan Ozbay.
Thank you, Ronnie, and you did a great job. Next time I'm gonna send like a much shorter. When you're my age, like you have a lot of things, so it's hopefully we didn't bore people with that information. I shared my screen and I'm gonna maximize. So I hope you can see my screen. So
yes, we can see it.
And Ronnie again has been a good friend for a long time. I've known him since his PhD days at UVA, and then as a professor. And I'm very glad to be able to give this talk about the work that we've been doing since probably March, April, COVID started. This is something new to me and to my group, but we felt as a responsibility, and we took some of our current work and redirected, and we're experimenting some things that we do not necessarily do every day, but this is not every day. So let me acknowledge my collaborators, my students and postdocs, Fanzo, Jingyin Gao, Zilin Bian. And there's also a couple of other people that I'm going to mention during my talk, Professor Joe Chow, Professor Oliver Gao also. So, I mean, this is a group effort. So I'm presenting on behalf of everyone else. I tried to kind of compile things that I thought the most important about our work on COVID-19. And then I also cited some of our most recent papers. So if you are interested in hearing a little bit more about the details, definitely you can look at the papers. Just a very quick introduction to our center. You have a similar center in Clemson. This is a Tier 1 center funded for 5 years in 2016. Our big team is smart cities. And like many centers, when you go deep, we do similar things like connected vehicles infrastructure, sensors, and resiliency. Big data, when you're in a city like New York City, obviously data is important. And also we are looking at these emerging modes of transportation like microtransit, micromobility, mobility as a service, and so on. And we have different faculty members, part of our center, working on these different problems. So it's not only NYU. We have Rutgers University, mainly working on the infrastructure resiliency. We have City College of New York. They work on most of these problems with us. University of Texas, El Paso, and University of Washington, Seattle. And we have a very good working group of faculty and other centers. I don't have time to acknowledge their names, but this is really one of our pride points, that we all work together as a group. One of the kind of things that we've been really trying to push, and I know Ronnie and his center has been very successful on that front, is test beds. And then we are continuously trying to build cyber-physical test beds for testing our ideas. And then our claim is that New York City, Seattle City is our basically living laboratory, living test bed. So this is basically kind of a big overview of the big data idea. So we are working on building an urban data observatory, we call it, because we feel like the foundation that everything that we do, including this work that I'll present to you, has its foundation in big data. And then we call that Urban Data Observatory because we are bringing data from different sources and we use it for performance measurement, systems, system monitoring, visualization and evaluation of operations, and then making long-term decisions. So from a very short-term operational decisions to long-term prioritization, investment decisions, we really work with the data. So this is kind of a snapshot of the urban observatory idea that we've been working on, and you'll see some version of that again, part of this work. We call it COVID-19 dashboard. And again, the idea is to be able to bring data from different sources. And then our priority is to use publicly available data so that we can make whatever we do available to researchers and stakeholders and so on. So this is the difference in this is that we are really curating large data sets and trying to make them usable to our agencies and our researchers. And then we're lucky that we have good relationships with different state agencies in New Jersey, New York, Seattle, and then we are using those relationships to bring some of that data and again, making it available to everybody else. So coming back to my talk today, I'm going to talk a little bit about the work that we've been doing for COVID. So I have to be aware of time here. So let me just look at my watch. Okay. So basically, COVID in big cities and all over the country, all over the world, it changed the way people travel. Also the transportation infrastructure, the demand, and everything else changed. On top of that, we learned new things like social distancing and how that affects the mobility. So there's a new norm of urban mobility in the middle of this pandemic. So we would like to understand that. The third bullet here that I'm talking about is we would like to really understand the relationship of a policy and what happens in real world. How long it takes for that policy to get a hold of, and then how people react to those. That's important because if we know that, first of all, we can tweak our policies. For example, I'll talk about policy to stay home. So do people listen to that? When they start listening to it in a way, we can really see the effects. And then what happens over time. So we wanted to use our data to understand that and use machine learning techniques to basically to be able to track these change points more accurately. So this is the first thing that we have done. We created so-called an interactive COVID-19 dashboard. And then we brought in data from related data. Obviously, we have a lot of data, but related data to the dashboard from different sources. So if you're interested, just please go to the this link, and then you will see the dashboard, the data, the visualization of the data. And the idea was basically to provide researchers, regular people, students, public, our stakeholders, to be able to see the data, to understand what's going on, and also to be able to download this data if they want to use that. And then you will see there's some interesting data sets in the dashboard, behind the dashboard, that people can kind of look simultaneously. So although this data available publicly in different places, this is one-stop shop for people to look at this data. We also created what we call sociability board. So this was the idea that we had with one of my ex-PhD students, Professor Hong Yang from Old Dominion University, and actually we have a couple of papers under review or to be presented. So to use the traffic cameras to monitor pedestrian movements and also vehicle movements throughout the city, New York City. So this is mainly New York City based, because many places these traffic cameras are on the freeways, and that's not very interesting. So you're interested in capturing pedestrians and people and other micromobility modes, and then these traffic cameras allow us to do that. So these are publicly available feeds. We capture those feeds, and we use image processing to understand the density or the social distancing of people, and provide that in a visually understandable manner. So these are, so we actually focused on two cities, New York City and Seattle. And then this is the type of data that we have: transit data, speeds, violations, and crashes, the volumes, bike counts. And I'll talk a little bit more about social distancing data, because this is something that's not readily available, but the camera feeds are available, and then we're converting them into data that's useful to us. And also in motion data, for those of you who are not familiar, there are sensors on the street that counts and weighs trucks when they're moving. New York City has few of these sensors. We have access only to one of them, but we also been working with NJDOT, and I said that a couple of days ago in a similar presentation. We're hoping to get that information in an aggregated manner, so you don't need to know every trucks to also see the truck movements, the freight movement. And then from that information, again, you create the type of visualizations that I show here, and they're interactive. You can go and filter data in a way you want to see. And for example, one of the things that got a lot of press during the COVID is crashes. So one of my research areas is accident analysis and traffic safety. So this, we were able to get that data, and then you can now superimpose that with the speed data and other data during the same time period, and then start analyzing if there's really a crisis of crashes, or increase in the severity of crashes, or is it that we are looking at them a little bit more clearly. So this kind of analysis can be done on the spot using our dashboard. So this is the architecture of our dashboard. So basically, we are getting data real time and offline, because some of the data is not available real time. So we get, like, for example, the taxi data from New York City Taxi Limousine Commission. It's offline, and they make it available, periodically. So we get that from them. It's publicly available. We put all of that together in a database, and then we integrate them. We process the data, and then we convert it into understandable analytics, and then present them on the dashboard. So if you look at some of the statistics in New York, I mean, this kind of justifies why we are doing what we are doing, because we were able to see, for example, that there's a huge decrease in subway traffic. And then if you look at from April to May, you continue to see that it's down. Same thing with vehicular traffic, but now recently vehicular traffic went back up to normal numbers. So you can really analyze and understand what's going on, which modes are really going down in terms of demand, which modes are going up. We can look at the speeds. For example, the speeds were up in New York. It doesn't mean much because the regular speeds, I think, during regular times in New York, 6 miles per hour. So when you talk about 100% increase, it's like 10 miles an hour. So it's not that much, but still for New York, it's a lot. And then that creates some locations, speeding tickets and so on. Okay. So now, right now, if you look at it, the current, and I ask my students to add like the most recent data, the subway demand is still very much down. So people are not using subway, same thing bus. So the transit demand is down compared to the same time before the pandemic. Vehicular traffic is down, but not that much, around 10%. So that's like becoming almost normal. Anyway, imagine understand that New York was very congested before the pandemic. So if the vehicular traffic is 10% down, it's not a big deal. It's still congested. The travel times are down, so that means getting congested. The traffic speeding tickets are up, but not as much as during the pandemic. Truck traffic is kind of a mixed, so outbound traffic is down, inbound traffic is kind of close to normal. And you see a huge increase in city bike trips. And we were talking before my speech, my seminar, people still not traveling, going to work. In New York, I mean, you have to go out because you live in small apartments. Looks like a lot of people are using city bike to do that instead of using the subway, for example. So we don't have like a clear evidence of that, but we see that city bike trips are up, and then the weather has been quite good. So I think this trend might go for a while. Okay. So one idea that we had, the data that we didn't have, is can we capture the social distancing in the city? So this is a paper that's going to be presented at TRB, and this is joint work with a bunch of different people. So how do we do that? So if you look at on your right, this is the view from a traffic camera in New York City. And then the other one is somebody took this picture showing that people, this is like at the height of the epidemic, came to watch the hospital ship coming to Pier 90. So there's a need to understand almost in real time the social distancing trends, pedestrian densities, and how crowded certain locations are. So I have some colleagues who got funding from NSF and other sources to send students out or record traffic or do surveys or collect data, but we felt this is not safe because during the pandemic, we don't want to send students out. We don't want to ask them to go and record traffic. Some of them are, I know some researchers, they have students or researchers with body cameras walking around recording. So we said, what is the alternative? The alternative is to use traffic cameras. And New York has hundreds of them. So if we can identify the ones that are strategically placed and then record that information that's available and that's being broadcast in real time, then we can maybe process that using deep learning based video processing algorithm. So that's why we have a large team, because we have people with different expertise. So we can use that improvements in image processing to detect images, to then convert that into distance projection approximation and calculate densities, and then fully automate this process without requiring anybody being outside in the field collecting data. So this is basically the overall idea. So we use the information from the traffic cameras, we store it, and it's a large data set, And actually, I think a couple of months ago, we had a scare because our server was down. Hopefully, luckily, we didn't lose any data, but we stored that data, which is not generally stored, and then use image processing for object detection, use post-filtering, post-processing filters to do a lot of interesting stuff, and then calculate pedestrian density and social distancing patterns that you see on the right side. So this is how the camera images look like. We chose 105 locations in New York City and one in Seattle. Why one in Seattle? Because most of, as I said, almost all the cameras in Seattle, they're on the freeways. In New York, actually, we have a lot of cameras inside the city, and you can really get a very useful imagery from these cameras, and then we can use that to understand how people are moving in the city. By the way, if you have questions, feel free to stop me and ask me. So this is basically a kind of a complicated process that one of my students, Fan Zhou, built. And one of the things that happened last 3-4 years, these deep learning algorithms became very efficient. So you see some of those here, like YOLO and Retina and Mask RCNN, and actually almost, and I'm learning this too because I'm not a vision person, but I did a project 6 years ago for AIG on a similar idea, using traffic cameras to do surrogate safety measures for traffic safety. So we used that same idea, but then at that time we wanted to, we didn't use deep learning. We used like a regular, well-known image processing algorithms, and we were not very efficient, and it was not very accurate. But with this new training data sets and deep learning algorithms, the accuracy is really good. So we tried all these three algorithms with different data sets. We also have a ground truth data set that we generated by using a certain part that we didn't use for training, and actually we found out the YOLO V3 worked very well, and we keep improving that. So one of the kind of contributions of this work is not just object detection, but how do we use these video camera images to calculate social distancing. So as you look at this picture here, with these traffic cameras, there are several problems. One of them is that they're not all focused the same way. The image quality is not very high. So that's one of the good things, because we cannot see people's faces, who they are, so there's no privacy questions. But that also comes with its own problems, because then it's not like a super sharp image. And also traffic cameras are not optimized in terms of where they're looking at, how they're looking at. They have sometimes funny angles. There's also this perspective problem. And there are ways to deal with the perspective problem, but one of the things that you have to do, you have to have some kind of a reference point. And with the AIG project, we did that. You go out to the field, and then you find an object for which you know the height, and then you kind of fix your images based on that reference point. Here, Fan adopted some of the well-known techniques. So instead of like a bounding area, he created a bounding cube, bounding box for pedestrians here. And with some assumptions, we can actually identify people and then put them, two pairs in one box. And then with some assumptions, we can assume that they are at certain distance in terms of pixels, and then we convert those pixels into actual distance. And then again, we do some in the lab with a bunch of undergraduate students, ground testing, and we kind of fix our filters to make sure that this distancing based on the bounding box idea works well. So actually, we were able to, when you're able to do that, we were able to measure the difference between pedestrians, and then that allows us to come up with the social distancing measures, and also the density. So we can count people, that's easy, but finding the distance was a little bit more difficult. And I think we did that quite successfully. So here, for example, we can just plot the density of pedestrians at some location for different dates. So the red one is before COVID-19. And now, I mean, most recently came back more or less, but like during like April 15, you see the yellow one is very low. But the more interesting one is these, the bottom ones, the round spheres. So here, the sphere, inside the sphere, you have number of cases at that time, COVID cases, and the length of the size of the sphere shows you the number of social distancing violations that we detected during that time. So here, this is a little bit counterintuitive. So what happens is when you have more cases, and actually the reason I have 3 of these figures, the number of cases inside the spheres are the same, but the sphere sizes are small because we make these violation decisions based on the distance assumption, less than 12 feet, 6 feet, and 3 feet. So this is like the most kind of conservative one. So let's look at this one because this is more clear. So what happens is when you have a lot of cases, you see that the social distancing violations are low. And these are the times where people are not going out, the density is low. And then when the cases start going down, you see the number of violations going up. So people kind of get relaxed more, and then they get to go out and they get like closer to each other and so on. So if you plot this in a time series, you might see these spheres becoming smaller and cases becoming higher. So there's definitely a relationship with some lag, which we haven't modeled yet, but that's very interesting thing to observe, how people behave in terms of their mobility in response to the number of cases in a certain area. So this is just one example of one camera image that we get.
Dr. Ozbay, I have
Yes.
2 questions in
Sure.
the chat box. So
Okay.
one is, are these data, hi, Dr. Ozbay. So are these data available from the New York City video data? Are these publicly available, the data?
So the data, so the data, you can go to New York City DOT cameras, and they're basically publicly available. You can see the video cameras, but you have to record them. I mean, you have to kind of capture them or scrap them.
That's what you did, right? You just use the publicly available data.
So they don't, obviously, they have no interest in saving this. So
Right.
we saved it and then we processed it, you know. So, and we're hoping that, I mean, we are still processing it. At some point, some aggregate version of this will make it available to the public, not the video data, but the counts and these social distancing violations and so on. But we're not there yet because data is still coming in and we're still trying to make this data perfect.
One more comment was that whether the slides will be available. So what we do for our C2M2, our center, we publish these whole presentations, the presentation in YouTube. So, and then if Dr. Ozbay agrees, then we can publish the slides as well.
Definitely. I'll give you a link to the slides so you can
Thank you.
Slides online. All right. Okay. So this is another picture. Basically, you see like a heat maps for pedestrians for different distance, assumptions. And again, from the same video, you can generate those. And this is, I mean, one idea that we have. It's not operational yet. So imagine you have this traffic camera, and actually we can run this image processing and calculation of social distancing in real time. Yeah, we can do that. We're not doing it, but or it can be pseudo real time. So you can like update this every 15 minutes. Then all of a sudden you see a number of violations, number of vehicles, number of person, just from the image, and that gives you an idea. So if you're a city DOT, for example, and you see a lot of people, like high pedestrian density, where you kind of think that that's not good, maybe you can put a warning sign, or you can make sure that people are keeping their distance and so on. So this is kind of a future idea, not happening. We're not saying it should happen, but if somebody's interested, the type of algorithm we have can do that, can process all this in real time. So, as I said, we are using a publicly available training set, but we know that New York City is different. We have a lot of high rises, big buildings. So we are creating our own training sets. So we have students who wrote an interface to basically create objects in certain locations, and then we can label things, or we can also find problems. For example, in New York, one of the bigger problems is the shadows. So we can, improve our filters to take these things into account and then retrain our algorithms. And the students wrote that little data collection tool, undergraduate students in my lab, and now we are improving it, and we're trying to make sure that we can create our own kind of site-specific training data sets, labeled data sets, for our own purposes. One of the non-COVID related thing that we are trying to do is that use the same algorithms, image processing algorithms, to recognize, for example, illegally parked cars or double parking, that kind of data that we would like to have. Again, as you see, you cannot see the license plate, so there's no privacy. But if there's parking on the bike lane, if there is double parking, and if you want to have some kind of statistical measure of this kind of violations in a location, we are hoping that we can get it from this kind of application, and then maybe find ways to quantify it much better. Okay, so now the second thing that I'm going to talk about is the lag effects. And I'm going to give you a little bit of information what I mean by lag effects. Again, this is going to be a paper that will be presented at TRB. And again, this is a large group because everybody's doing different things. So let me just talk a little bit about that. So, the social distancing and other orders now became kind of standard. No? So in many cities, they say, oh, you cannot go out after dark, or like you cannot go out if there's no emergency. So we would like to understand how these different announcements by the government are being implemented, and how people are responding to that. So when you tell the people to do something, how long it takes to see the effects of that. That's important because we are assuming that our hypothesis is not immediate. So does it take like 2 hours, 2 days, 2 weeks, or as people, do they listen to it? So we'd like to really see that from the data. And the other thing is which is we spend less time on that, is basically to look the lag effect for implementation. If there is an emergency, how long it takes for the government to make an announcement. So this is basically, we call it implementation lag. Again, those ideas actually have some other applications other than COVID. For example, think about evacuation. How quick do you have to give the evacuation order to see some impact? So if we have the methodology that we are talking here, used for these kind of applications, I think policymakers can learn a lot. So this is two lags that I talked, like impact lags and implementation lags, that I will talk a little bit more about. So to do that, we are using so-called the change point detection framework. So this is actually well-known technique in machine learning and statistics. And then we want to quantitatively estimate the implementation and impact lags for COVID-19 related policy events. And then maybe provide some kind of lessons for policymakers that can be generalized for future use. Unfortunately, now we are hearing like a second wave, third wave, fourth wave. So this is not going away anytime soon. So whatever we learn from the historical data, we hope that it will be used to make things better in the future. Again, these are the two data two cities that we are dealing with. For New York City, we're using the vehicular volumes, bus ridership, subway ridership, and bike ridership. And luckily, we have very good data from New York City about all these different modes. From Seattle, we have two locations for which we have the vehicular volumes. And this work is joint with Jeff Pan, University of Washington, Seattle, and his students. We have transit app usage, and then we have bike ridership data from Seattle. So if you look at the major policy timelines, we try to kind of put them in a visually readable format. So they're similar for both cities, but there's some time differences. And again, what we want to understand is that what happens when the city of New York declares emergency? Do you see a change point in terms of vehicular demand or transit demand? And then subsequently, maybe like a week later, there is U.S. emergency declaration. Again, do we see a change? Do we see a further change? What happens? And on and on. So how all these policies are changing our mobility system. So that's what we are really trying to figure out. And how fast we see that change, and then how much that change continues before people start, for example, doing something else. So can we automatically detect that? Okay. So on the left side, it shows all the data that we are getting, and then we are using different methods for change point detection, and then we are finding the policy lags and then impacts on the transportation system. So I'll talk about each. We tried three different policy change point detection techniques, and I'll talk about each of them a little bit more. So what is this change point detection? So you can formulate this as a very simple problem. So you assume that you have a time series data, multivariate data that's coming from a random process over some time. And then what we are trying to do is we're trying to find if there is a breakdown. If you look at this figure, if there's a breakdown in the way this data is coming, so and that would be determined as a change point. And of course, you want to do this automatically, and the way to do this automatically is basically to set it up as an optimization problem and minimize this term. So basically, some cost function for the sum of these clusters, plus some penalty for the complexity of the cluster. So if you have too many of them, you add some penalty. So you don't want to have like a very small clusters. You want to be able to find the optimal number of clusters. And then this cost VT will depend on the homogeneity of each segment, how homogeneous, how optimally can be divided so that each segment is as homogeneous as possible. Actually, going back to 15 years ago, we used a similar approach for sensor placement on freeways. So finding the homogeneous freeway sections, and then say that on that section you can have one measurement and it will measure everything on that section. So it's a very similar approach, but at that time we used k-means clustering. Here we will use different ideas. So we tried basically three different ideas. One is this pruned exact linear time method, which I'll talk a little bit about. The other one is the breaking point method, then Bayesian change point detection. The reason we tried those because they all have different strengths and weaknesses, and they basically perform differently on our data set, which is the time series data for travel times, demand for transit, demand for bike, and so on. So as you can visualize, these things change in time. So today there is 100 vehicles that are used, tomorrow is 150, 160, and then you look at the time series data using these different methods and then find where is the change point, basically. So the PELT method was good in detecting change points, and that was what we wanted. But the BP method, the breakpoint method, also was not bad, but it was too sensitive to change points. So it was, we had to be careful using all the change points it predicted. And then we used the Bayesian change point method, which is a continuous method, as a reference, kind of to validate the previous two. So the likelihood ratio, the PELT method, is almost creating a tree. So if you're familiar with card trees or decision trees, so basically you take your data set and then you kind of cluster them like a tree based on this decision function, the objective function. So basically you start with some kind of a cluster and then you add more data on it with some cost function. And if it is, it increases your total cost function compared to the previous cluster, you say, maybe I need to create another split because this is not making my a cluster homogeneous. It's like as a cost. So you create another cluster and then you keep doing that. And then if you look at down, you can create this change points for using this method. Very simple method of breaking the data into clusters, basically using this cost function. Okay. So the other one, which is also very straightforward, this is regression structure method breakpoint. So basically here what you claim is that if I have a regression function that I predict using certain amount of data, so I get like the beta and delta variables, I estimate those. But let's say I add more data on top of it, and then now these parameters that I estimate are not the same parameters I estimated statistically, obviously, with the previous cluster or data bin. So basically, then I say, okay, this is not the same regression function. So there's one regression function for this bunch, and then there's another regression function with this bunch. So basically, by looking at the stability of the regression coefficients, I decide the breakpoints within which these regression coefficients stay stable. And there are different methods to do that. And of course, it's all iterative. So I can calculate these regression functions, and then I can find the sum of square residual errors for each regression function for the data that's applicable to it. And I then do a little bit differently and find the sum of squared errors. And then I choose the combination that gives me smallest sum of square residual errors. So basically keep trying, but it's not blind. We can use Bellman principle. But I mean, this is an old paper actually from 1969 that people forgot about, and it was discovered. And it's kind of interesting method. So the third one is the probabilistic method, the Bayesian change point detection. So in this one, I'm going to give you an example. I can divide my data set, which is observed data points, D1 to Dn, into basically two segments. Okay, so it's just problem is to finding where is this tau? Where do I break my data point? And then I can set it up as a Bayesian problem. So this P mu1, mu2, sigma tau, given my data, is the posterior function that I want to find, and this is the Bayesian conditions. So this is kind of difficult because there's too many variables here, but these variables mu1, mu2, and sigma, I'm not interested in them. Okay, so I can marginalize this function, and I can write it as P tau conditional to my data, and then I can calculate it using MC iterations, and then I find the best distribution for that bunch, and then in the end. I will have these solid lines as calculated by the MC iterations. And then you see I have my data points. So basically the solid line says there's no change. for these data points, and then it goes down. So it says, so there's no change here, and it goes down, and then for a while it gives me the trend. So this is not like it doesn't give me one change point, but it gives me kind of the continuous trend. So if I compare it with PELT or BP method, for the PELT or BP method, I get one big change point detection and the other one and so on. But here I get some kind of a continuous representation of the trend of change. I mean, this is the kind of long, short story for much longer effort. And then we took all these methods and applied them to our data set. So this is our, let's say, vehicular traffic for different days between March and June. And then if you look at the daily volume, so I plotted basically the policy, the time the policy was issued. So the blue one, the blue one is basically New York emergency declaration. The dark blue is the U.S. emergency declaration. The light green is the gathering ban, and so on. Okay. Now with PELT and the breakpoint methods and so on, I'm finding now the breakpoints, and as you see, I mean, they're kind of similar, but these are easier to look, breakpoint methods. No, so it says this is one change that happened, and this is little after the gathering, the ban, the gathering ban, but it has a lead to the pause order. So there was a change in the daily volume even before the pause order. The traffic went down drastically. So people kind of anticipated that, and then they stopped using their cars. And then for a while, there's no change. And then like a month later, maybe more than 5 weeks later, I see another change point. And this blue one is the confidence interval. And then this is a little bit even before the midnight subway closure. So again, maybe things are getting even worse. So the data shows that people kind of anticipated. So there's a lead and so on. So I can do the same thing for the bus ridership, and then see the events when they happened, and then how people reacted, how fast or how slow they reacted by using my change point detection. Okay, so here I'll read that for you. The declaration of emergency increased the city bike usage for about 8 days by more than 40%, and then it dropped for a while. And then the midnight closure of the subway and New York City open streets, which I mentioned, had an immediate effect with city bike ridership. So I can just look at this data and I use my machine learning algorithm to find the change point detections and then see how fast they move. So this is Zilin put this in a very nice format. So basically, this shows me how fast or how slow a change occurred for different modes. So, for example, for the vehicle, it was 6 days before the emergency declaration, and then there's like some lead time, But for U.S. emergency declaration, it's 0. The moment the declaration happened, we see a change point. So it just very quickly, people quickly responded to the emergency declaration from U.S. For New York, there was different. And then you can look at all these different lead and lag times as identified from our method versus the time the policy was issued. So, for example, let's look at the pause. Had long effects that kept. So for a long time, the pause order affected people, like a 35 days for traffic, 40 days for bike, for 64 days for bus, and so on. And then after that started to increase. So it took effect quickly and then stayed there, and then for a while. And then after that, we see another change point. In this case, they start increasing. We did the same thing for Seattle, but as I said, for Seattle, we have limited data. So if you look at the transit app data, it doesn't really make much sense because our data was very limited. So here, what we are claiming is that for traffic, we got meaningful change points and that were in sync with what happened in terms of policy. But for the transit app data, which was very limited, we didn't get good results. Okay, it was too sensitive. And then we have a similar kind of representation of lead and lag efforts for Seattle. Again, a little bit less confident. I'm less confident about this because I don't have as much data, but still they're comparable with New York City. One thing that we saw for I-5, it's a residential area, at a shorter time effect after stay-home order than SR99. It's another location for which we have the data because SR99 was close to many high-tech companies. Actually, they acted before the stay orders. The tech workers started staying home even before what the government enforced policy became enforced. Okay. The implementation lag, as I said, is another idea, but it's we haven't spent too much time on that. So here, what we are looking at is that if you have the number of cases, hospitalization numbers, what is the relationship of that to stay-home order? So how fast the government react when they see the number of hospitalizations? So actually, if you look at it here, so this, so these are the number of hospitalizations, and actually government acted pretty quickly. And if you look at the pause order, it's almost exact same time as our change point detection from the algorithm. So government issued this stay-home order when we identified the point where we identified the change point. It means the cases were now going up very quickly. So the government reacted very well. So this is basically, this gives you an idea how well the government reacts and how quickly the implementation order, the order is implemented as a response to what's happening in this case in terms of hospitalizations. Okay. So our lessons learned basically, I talked about many of them. The magnitude of impact on vehicular traffic system over the time period, we can use those to better understand and tackle the change of traffic system for outbreak. So basically, we know how fast and how early we need to make the policy announcement to have an effect. So this kind of gives an idea. Transportation agencies, then they can use this information to maybe to run their system better, maybe to reduce congestion and accidents, because this is one of the things. So the agencies didn't know how fast the demand is going to go down and the speeds will go up. But if they know that it's going to take a few days, so they can improve the enforcement and then maybe increase ticketing and other activities to reduce accidents. So the other thing here, we saw that different modes work differently. Of course, this is conditional to the type of the emergency that you have. So that means you have to have different resource allocation and planning activities for different kind of modes. So one thing that we saw in all this exercise, there was a very increased demand for bicycles, micromobility. So if you can predict how that demand is going to go up very quickly, then you can basically make sure that you have spare parts, you have additional bicycles, additional micromobility devices to respond to that demand. So what I'm going to do, I'm going to finish. I know I'm running a little late. A few slides about our work on the modeling side. So we have a MathSim agent-based mobility simulation model that we have developed. And this is Professor Chow is in charge of that. And then we wanted to use to see if we can evaluate COVID-related scenarios. So what is the challenge here? The challenge here is that this model is calibrated using normal time conditions. So can we use our data that we are collecting to quickly recalibrate to capture COVID-related situation? And this is exactly what we have done. This is a very detailed agent-based model for 8.5 million people in Manhattan and non-Manhattan segments. And then there's actually a couple of papers coming up. So you see like how it works. So this actually builds strip chains. So it's not just OD demand matrix, but it also builds the strip chains for each agent. So it's a very demanding model. So what we did is we took our COVID-related data when it became more available, the data that I spent like an hour to discuss, and then recalibrated it for recalibrate the model to reflect the changes in subway demand, driving demand, and walking demand. And then used it for scenario analysis for before COVID and after COVID conditions to see what happens, for example, if you run the transit at full capacity versus if you reduce the transit capacity by 50% to allow for more social distancing, what happens to car traffic, what happens to transit demand, and what happens to micromobility. So one of the things in this kind of model, we can model modes that are difficult to model in other tools like Cube or ME2, whatever. So we can model micromobility, for example. So what we saw is in our model, the car demand went up to 150%, 140%, but not more than that because there's no capacity. Transit demand fell down by 64%. And then there's a big demand for city bike and everything predicted by the model. So this allowed us to kind of see how these changes will happen for different kind of scenarios, especially operational scenarios, like what happens you change your transit. We also tried it for different congestion pricing scenarios and so on. So the policy implications is that this model allows us to test different policies like congestion pricing and different kind of flavors of it, like cordon-based pricing and so on after the COVID reopening. So it allows us to kind of make better decisions. It shows us that micromobility will be, the demand for it will increase significantly. It also shows us where the increase is going to happen. So you can really do some resource allocation for those places. And then what is the optimal level of transit that minimizes the possibility for infection, but also maximizes the mobility. So it allows us to run this kind of scenarios very effectively. So with that, I'm going to stop and then see if there are any questions, anything that I can answer. So I think I'm on time.
Thank you, Dr. Ozbay. Thank you very much for a very informative presentation. So please ask your question to the speaker, or you can write in the chat box.
Yeah, let me see if I can stop sharing.
So
and I can see the chat.
There was one question, Saki, based on your observations, what are the prominent long-term effects of COVID-19 on New York City transportation system?
So right now, what we see is that, as I said, the car traffic almost went back to normal, but subway and bus demand is still very low. So I cannot say in the long run, but in the midterm, I think there's going to be less demand for transit, which is not a good news for New York City because New York City depends on transit and there's not enough capacity for cars. But also we saw that there's increase in bike demand and micromobility, like scooters and so on, shared mobility type of stuff. So there's increased demand for that. So personalized modes are getting more demand, and the mass transit still is getting lower demand, much lower than pre-COVID cases.
Any more questions? So please type your question and just speak up, please. Yeah, there's one more question.
Okay, yeah. So the question is that from the change point detection, we see that different modes have different change, change points. Why do you think the reason for these differences? Again, so it's not very explicit, but it's explicit in the data. This is the conditional to the crisis. So this was something different. Obviously, it would have been different. No? So in here we are talking about pandemic. So people, they don't want to be too close. So the response for different modes is dependent on that. So people basically they don't want to use transit, and then they respond to it very fast. Maybe for car takes a little longer because they feel more comfortable to come to the city in their cars. But then, as you saw, when there's a U.S. announcement from the federal government, everybody stopped traveling. So depends on who is making the announcement, the policy announcement, and then what kind of mode we're talking about. So it's mode specific, and also the source of the announcement makes a difference. Also the location. For example, in Seattle, we saw that all these high-tech companies reacted much earlier than the government and told their employees stay home. So you see a lead time. So people started staying home, not traveling before the announcement is made. So it's all depending on different factors. Who makes the announcement, where it is made, and what kind of transportation mode we are talking about.
So Dr. Ozbay, I have a question. So in your team, so you analyze the data, and you came up with some results, but did you include any policy analysts or professors or researchers in policy who looked at the data in terms of policy implications?
So we are not making policy recommendations.
Just what it means, yeah.
So what we want is we want to give a methodology to policymakers, and we want them to use it. And these are relatively simple methodologies to use, but we don't claim to be policymakers. We work with a public policy school, but they were not involved in this work. But our hope, the data-driven analysis and also the MATSIM, agent-based modeling analysis, I think both of them, they are powerful approaches that the policymakers can use. So MATSIM actually has been used by others for a long time, but I think this is the first time it was recalibrated almost in real time when the event is happening, and then used in a recalibrated manner. So we wanted to show the feasibility of doing that. And again, we want the policymakers to come and test their policies and then use our results for making better decisions. But we're not claiming we're going to make policy decisions.
Okay. Any other question for Dr. Ozbay?
So this is like my class. It's a quiet crowd. People have, I guess, Zoom fatigue, So, but that's fine. Please feel free to email me if you have any questions. If you wanna, access to the dashboard, or if you wanna see copies of the papers, I'll be glad to help all of you with that. Okay. Thank you, guys. Have a nice weekend and afternoon. I hope you learned something. All right. Thank you.